one electron goes down. Okay, this is called the orbital diagram. Where do we get this from? The Pauli exclusion principle. The next one is a 2p. Now, each seat, kind of like a regular bus, only fits 2 electrons. 1, but you have 6, 2, 3. All of this is part of the 2p. And the Hans rule says that each electron must spin in the same direction before it occupies a second electron. 1, 2, 3, 4, 5, 6. One is spinning up, the other one's spinning down. And yes, it's a half an arrow. I don't know why. The next one is a 3s. 1, 2. The next one's a p. How many seats are in the p level? 1, 2, 3. All of this is the 3p. How many can fit here max? 6. Do we have 6 electrons? No, we only have 4. What does the Hans rule says? The Hans rule says orbitals of equal energy must each have 1 electron with the same spin before an orbital occupies the second electron. So 1, 2, 3, 4. Okay. Let's answer a few questions here. How many energy levels in an atom of sulfur? How many energy levels? Who's the energy level? The energy level is the large big number. I have a 1, I have a 2, a 2, a 3. How many energy levels? I have 3 max energy levels. I don't go any more than that. How many orbitals contains electrons? Okay. How many orbitals contains electrons? Well, let's see. Here's one orbital. Here's one orbital. 1, 1, 1. There's 3. Here's 1, 1, 1, and 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, how many electrons are unpaired? Ooh, 2. How many electrons are in the second energy level? Who's the second energy level? The big number, right? So how many electrons are in the second? Not this one, because that's a 1. This is a 2, that's a 2, that's a 3, and that's a 3. So let's count up all those electrons. How many do I have? 2, 4, 6, 8. 8. Okay. Iron, gold. And then we're going to talk about the shortcut method. And you saw the shortcut method in the video notes, but we will practice that as well. Okay. Then we're going to go talk about ground state versus excited state. Okay. When the electrons are jumping because they got excited. And then we're going to go to the last part. And the last part is talking about waves. Okay. And we're going to talk about Planck's constant over here. A little bit of math. It's not difficult math, but it's math. And then that's it for our notes, okay? So let's go ahead, and I'm going to leave those 2 for us to do in class. Let me find my highlighter. Oh, that's not it. Here it is. So we'll do this one and this one in class, okay? And then the shortcut method. We'll do the shortcut method and talk about those as well in class. We've got to practice, okay? And then let's talk about the next part over here. Ground state versus excited state. Now, ground state is the most stable or the lowest energy arrangement of the electrons in an atom. Okay, excited state is when an atom gains energy and the electrons jump into higher energy levels. So it says here, recap. Electrons go from ground to excited. When this happens, they absorb energy. Electrons go from excited to ground, from high to low. They are going to release energy. And they do that in the form of light. Okay? We say that a photon is emitted. Okay? A photon is emitted. That's what we call it. It says here, identify the following atoms and describe their state. Is it a ground state? Are they in ground? Or are they excited? Okay? So in this case, let's look at it. First step is you need to count all the electrons. We got to figure out who we're talking about. So 2 plus 2 is 4 plus 10. 6 is 10. Plus 2 is 12. Plus 6, 16, 18, 19. Plus 10 is 29, 30, 31, 32. Okay, so we're at 32. Well, let's go to our periodic table and let's look at 32. Who's 32? Right here. Germanium. Okay, so he is GE. That's who we're talking about. GE. Now, GE, we need to figure out if he's excited or if he's grounded, like normal, like he should be. Okay, first thing is, there's a couple of steps here. The first thing is, let's go ahead and let's look if everyone is where they should be. So let's go back again to, I thought I wrote it over here. I guess I wrote it on a different set of notes. Page 1. Let's go back to page 1. On page 1, I wrote it, but I wrote it somewhere else. Here it is. I said over here that S's can hold 2 electrons. S's, there's only one S, that's it. It can hold 2. The next level has an S and a P. It could have an S and a P, and the max is 8. Well, if I know if it has an S and a P, and an S's can hold 2, 8 take away 2 is 6. So P's can have 6 electrons. Okay? Now, if this one has an S, a P, and a D, and there's 18, if out of 18 of those, if 6 of those belong to the P and 2 of those belongs to the S's, okay, 6 plus 2 is 8. How many are left over for the D? 10 electrons. Does that make sense? How many electrons can be in an F suborbital? Well, if there's 32 electrons for an S, a P, a D, and an F, and 10 are to the D's, all right, 6s belong to the P, and 6 of them belong to the P's, and 2 of them belong to the S, so that's 16, 17, 18. So 32 take away 18 equals, well, how many is that? So that way we can figure out what's going to belong into the, what letter are we talking about? F. The F can contain up to, do you know? F can have up to 14, right? 8, 9, 10, 11, 12, 1, 2, 3, yep, 14. So, knowing that information, I'm going to write it over here. S's can have 2 electrons. P's can have 6 electrons. D's can have 10 electrons. And F can have 14 electrons. Now I'm back to the same page that we were originally. Step number 1, to look to see whether it's grounded or excited. I'm going to come over here and just put step 1. That's what I'm going to do. I'm going to look to make sure that the S's, the P's, the D's, the F's have the correct amount of electrons. What do you mean? For an example, this is one S. How many electrons should be behind the S? It should be 2. If it's not 2, then this means that it's going to be excited. This is the first easiest step to decide whether or not my electron is excited or grounded. Let's keep going. 2s2. This S can only have 2, so that's correct. P's. How many can P's have? 6. It has 6, so he's good. The next one is a 3s. How much? 2. 2 is good. The next one is a 3p. How much should P's have? 6, and it says 6. 4s. Whoa. S should have 2, and this one has 1. That right there is proof that GE is excited, because that other electron is in the wrong place. He jumped. He got excited. Okay? And so that is really one of the easiest ways to go through this and figure it out, pretty much. There's a few other ways to do it, but that helps me out. Let's keep going. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, 19, 20. 20 plus 10 is 35. Who is 35? 35 is Br, bromine. Br. Is he grounded or excited? Well, what is pretty much the number one thing that we do is that we look at the S's, the P's, the D's, and the F's, and they should have the correct amount of electrons. And we wrote them down over here for a shortcut, and we wrote it on the front page. S suborbitals can have 2 max. P suborbitals have 3 seats, and each seat can only contain 2 electrons. So 3 seats, 2 electrons is a max of 6 electrons total. The D level or sub-level has 5 seats, and each seat can contain 2 electrons, so 5 times 2 is 10 electrons max. F, 7 seats on this level, sub-level. Each seat can contain 2 electrons. 7 times 2 is 14 total. So let's go ahead and let's look. 1s2, correct. 2s2, correct. 2p, P should have 6, correct. 3s2, correct. 3p6, correct. 4s2, correct. 3d, 10, correct. 4p, well, it should have 14, Ms. Munson, and this one has 5. Okay, let's count them up. Well, we counted 35. At the end, is there any left over? There was only 5 left over. And so just like this one over here, remember, there was only a few left over. We didn't have all of them. So we didn't have 6 here. We only had 4. And that's okay because that's all you had left over. He used up what he had left over. He is grounded. All right, let's do the next step here. The same one. Same step. Next problem. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 6 is 36, plus 2 is 38, plus 8 equals 38, 39, 40, 46. Ooh, 46. Put that number down before I forget it. Go to our periodic table. Who is number 46? Palladium. Palladium is PD. PD. Okay. Well, what is pretty much our number one rule? Our number one rule, and I will show you a shortcut later on, but as of now, our number one rule is to look to make sure that all of the S, the P's, the D's, the F's have the correct number of electrons, and we start from the lowest level and we move our way up. Everybody should be happy and full. If somebody is missing or is incorrect, then that means that an electron was missing. He got excited and he jumped to another level. So let's see. 1s2, correct. 2s2, correct. 2p, how many should be in the p? 6. 2p6, correct. 3s2, correct. 3p, how many should be in the p's? 6. 3p6, correct. 2s2, correct. 3d, how many should be in the d's? It says right here 10. 3d10, correct. 4p6, correct. 5s2, correct. And then 4d8. That's just because there wasn't enough left over to make it 10. So that's okay. This is grounded. Easy, huh? I'm going to show you another way to do it. But this right now is going to be the main way that you're going to do it until I show you the new way. Okay? Notes. We're still going with our notes. Next part over here is a few vocabulary words. Frequency. The word frequency means how many waves or how often do you go? How often is it there? How frequent? Okay? So, frequency is the number of waves that pass a given point. Now, what we do need to know is that the SI unit for frequency is a H, capital H, lowercase z, hertz. Velocity of a wave is the speed of the wave. And we need to know that the SI unit is going to be in meters per second. Velocity of all waves in a vacuum. Now, let's make sure that we understand what they mean over here by this word vacuum. A vacuum is when there is no matter like air molecules. Like there's no air molecules. There's no matter. Okay? Example, in space. Right? When you go to outer space, those astronauts have to put on a spacesuit because there's no matter. They're considered to be in a vacuum in outer space. There's not even any oxygen for them to breathe. Okay? Now, the velocity of not just any, I mean all waves in a vacuum have the same speed. Which is the speed of light. Oops. Oh my goodness. I really destroyed how to write that. Now, the speed of light as of now is the fastest thing known to us. We can't travel the speed of light. Our bodies can't handle that kind of speed. We have no technology here on Earth that we can make or have been able to make that has been the speed of light. Now, we can break or we can go faster than the speed of sound, which is not as fast as the speed of light. Okay, and whenever planes can go faster than the speed of sound, that's called what we call a sonic boom. Okay, so there are some airplanes, some jets out there that we have that can travel faster than the speed of sound. And when they do that, we say that they broke the sound barrier. Okay, they produce a sonic boom, but we can't travel the speed of light. That's the fastest thing known to us. Now, the velocity for the speed of light is 3 times 10 to the 8th power meters per second. The shortcut is a lowercase c. Okay? You don't need to memorize this because this is absolutely on your formula chart. Okay? And if you have seen E equals mc squared, that little c from Einstein is the speed of light, c. Okay, now we're going to talk about an equation here, and our equation for us that we're going to use is c equals f times lambda. Frequency is abbreviated by a f, which is that. The speed of light abbreviation is a lowercase c. And this little weird squiggly thing is what is a Greek alphabet, I think it is. Well, Greek alphabet, from the Greek alphabet, it is. It's considered to be, it's abbreviation for a wavelength, which is going to have an SI unit of a meter. And we call that's called a lambda. Okay, that's just a regular F for frequency, right? And that's going to be in hertz. We said that up here at the top. And C stands for the speed of light, which is meters per second. Ready? One thing that we do need to know is that lambda, wavelength, and frequency are inversely related. And I do not know why that should be that little weird symbol. Are inversely related. The word inversely, what does that mean? Opposite. What do you mean? Well, if you look at this one over here, from crest to crest, or from the top to the top, look how big distance that is. Look over here from this top to this top. Look how short of a distance that is. Okay, so on this side we have a what we call high, big. See how big this lambda a big lambda. Big wavelength. And over here we have short wavelengths. Short lambdas. And on this side we have low energy. And on this side we have what we call high energy. On this side the frequency is low frequency, and on this side we have high frequency. So lambda, which is wavelength, and frequency are opposite of each other, and I do not know why I wrote the lambda sign. There should be an F for frequency. Who knows what I'm thinking. Are inversely related, and you can see it. Look, high frequency, high wavelength, low frequency. Low wavelength, high frequency. Okay? So for an example, I'm going to draw a wave. If I start here, and I go to here, and I go up, I go down, and I go up, and I stop right here. Now I'm going to draw a wave over here. I'm going to go up, down, up, down, up, down, up, down, up, down, up, down, up, down. I think you get the point. This side over here, I try to make them the same height, and I try to make it go all the way down to the same. Do you see what I'm saying? I didn't want that to be anything with us here. I didn't want you to consider and look at how high it goes up or how. I want you to consider this. See how far apart this is? So from here to here, that is considered to be one wave. Down, up, one wave. Let's look at this one. This one goes first, up, down. That's one wave. See how it's smushed in more? Okay. And on this side, we have this bottom part of the wave, and we call the bottom part a trough. Okay, whether it's here or whether it's this trough, they're both troughs. The next one we have, then another part is called a crest. A crest, like an ocean crest, the top of the wave. Is the top of the wave here or the top of the wave here? So from here to here, we call this wavelength. This is a long wavelength. From here to here, that's a short wavelength. They both have crests, they both have troughs, but I can see that this long wavelength, right, lambda, also has very low frequency. How many, during this section, how many waves passed? 1, 2. It was only frequent 2 times. Within this section, how many waves passed? So from here to here was 1, from here to here is 2, 3, 4, 5, 6 and a half. So this side is 2 waves. This one had 6.5 waves. So this one had a high frequency. It was frequent 6.5 times, but the lambdas or the wavelength are short lambdas or wavelengths. They're smushed in, they're close together. Okay, if you have any questions regarding this information, again, I know we're starting to hit some new stuff that you probably may not have really talked about prior to now. Okay, there's a little bit of math to go along with this, and then we have another equation as well. All right, I'm going to pause the notes right here, and I will come back on the notes, finish them up tomorrow, and then I will post these so you can have them and watch them on Monday. All righty.